Um, Thank you, Lorenzo, and thank you, Alexander, for this kind invitation. So, actually, I think this is the very first time that I will be giving a talk at any kind of machine learning events. I'm not a machine learner, I'm a mathematician. But very recently, I had quite, like I would say, a fortune to collaborate with some of my high school friends. And two of them are in Cambridge right now. So they are actually in University of Cambridge, Challenger in Shubhayon. And they were actually visiting UC Berkeley at some point. Both of them were there, and I was at Stanford, and we had a chance to hang out and discuss some problems. That's how really this thing started. And so yeah, and I believe like Challenger has presented this work at a few other venues. Um, so some of you may have seen some aspects of this work, but I think there has been some more updates. And so I will be focusing on some of those new stuff. And also I will definitely talk about some of the old results, which are kind of interesting for people who haven't seen it, just for completeness. And then finally, I will talk about one problem that I'm personally working on and my main motivation why I started working on this. So, and that will be an analyst point of view. So I do think, so I come from an analyst background, so I have some interest in finding inequalities for analysis and so on. And it's a big thing. So anyway, so let me just talk about the thing. So there is actually an archive paper on this, which is really a V1. So we are working on V2. Some of the new results that I'll present you today are not in the V1. But yeah, but it's work in progress. Okay, so let me just say, so this is my main motivation. So there exists a lot of examples in mathematics where one has a nice inequality derived under a specific set of assumptions. And this really is my way of looking at the problem. My collaborators have their own motivations for looking at the similar problems, but really this is my point of view. And basically one would like to know how a particular inequality generalizes and changes when some of the assumptions are slightly altered, or let's say you add some new assumptions or you take out some assumptions, and really like you want to know how a certain inequality changes. Let's say you change the dimension, for example, then you want to know what happens and so on. So really these are questions that mathematicians kind of have to deal with on a day-to-day basis. And so the question there is like, can one design a scheme that can help us in such a search? And really the goal here is to make the daily job of an inequality hunting mathematician easier and faster, and basically add a computational toolbox that they can leverage. So maybe this toolbox will not exactly spit out conjectures, but it may give you things that are true. Let's say. So this is really conjecture, so it may or may not be true, but it will give an working mathematician an idea like what could be true and what would be some ways to generalize some of the inequalities that they're trying to generalize. So yeah, so we make some preliminary headways towards this problem. This is most definitely work in progress. Okay, so the way we formalize this problem is as follows. So we start with something called the space of relations. So the basic setup is this. So we have D, which is like a finite dimensional vector space over, sorry, this should be the real numbers. So this is not scriptor, but bold-faced star. And we assume that D has, let's say, this is an n-dimensional vector, so something like Rn, let's say, and over real numbers. And suppose the setting that we are going to deal with is going to be a compact subset of D. So D hat is going to be a compact subset. And this compactness assumption is important for some of the things that I will say. In practical computational problems, the D hat will be like a discrete set of points. So it is definitely a compact subset. But this is how I formalize things. And we'll call this the features. So basically, this is things where our data is going to come from. Okay, so once we have this, we are going to start with our space of continuous functions on D hat, which we all know is a Banach space. So any the set of continuous functions on a compact subspace of Rd is a Banach space. And it comes with this, equipped with this supremum norm. So that gives you the Banach space structure. And the space of relations is basically everything that is in this product space. So here we think of tuples. So two continuous functions f and g will be a point in your space of relations. So in general, f and g can be arbitrary, like there can be no relation between them, okay? And in this product space, this is the natural, the norm structure that you impose, that you get from your CD. So on this product space, this is your norm. So this turns this into a Banach space. Okay, so once you have the space of relations, you can specialize to something and define our conjecture space. So this is our specific definition of the conjecture that we are working with right now. And this is slightly different from what we have in the paper because, okay, this is a improved version. So what we say is that, okay, so we start with elements in the space of relations. And we say that a tuple is going to be a conjecture if and only if one of these conditions hold. So sorry, so this is going to be fx less than gx and fx greater than gx. Either of these conditions should hold. So there is a typo here. And this is the set that we call the space of conjectures. So C less than equals a disjoint union with C greater than union is called the space of conjectures, where C less than equals is this set. So this is all points in your space of relations such that fx is less than gx for all x in your compact set where your basically data comes from, and the other way around. So this is, but this sets a disjoint, which you can see immediately. So, so this set is what we call to be the set of conjectures. And it's an easy consequence that once you have this definition, so all these three sets like C less than equals and C greater than are all open subsets of the space of relations. And each of them is a Banach manifold. So why is this a Banach manifold? So this is a simple proof. The idea is very simple. So first of all, since R is a Banach space, it is a Banach manifold by definition. Any open subset is a Banach manifold, and these conditions are open. The condition f less than g and f greater than g are both open conditions. This uses the compactness of d hat. So this is, for example, one place where d hat comes in. So for example, if you replace less than equals to less than, so if you replace strict inequalities with like greater than equal or less than equal, then this open condition is going to fail. So you are going to have some extra complications. So that is also something that we're trying to resolve, but that's like not going to be part of this talk. But yeah, equality conjectures is something that is also of interest in lots of cases. In any case, okay, yeah. So this C greater than equals and C less than equals, these are both open sets. And since open sets of a Banach manifold are themselves Banach manifold, so that's it. So you conclude that your space of conjectures is going to be a Banach manifold. And yeah, so there are basically two connected components, and you can also show things like these are convex sets and so on. Okay, so one should note that this compactness assumption gives you something interesting. So any point that you pick from your conjecture space, the infimum over this compact set, there will be, this infimum is always attained, and this is going to be a number that is greater than 0. Okay? So, so I mean, that's basically the main reason why you have these open conditions. You always have some room because of this because of this compactness assumption. So really, this thing that lets you prove this condition. Okay, so I think for some of you that might be obvious. In any case, so now what we want to do is like, so what is the overarching goal then? So the overarching goal is that we want to find these points which are in our space of conjectures, which is a subset of our space of relations. And the question is like, how do we do it basically? So what you can realize is that not all points in our space of conjecture are sort of giving you new information. So for example, if I give you one conjecture fg and some another conjecture, let's say f prime g prime. So you can, for example, add both sides of this inequality. So let's say f is less than g, for example, and f prime is also less than g prime. So you can, for example, add f plus f prime is less than g plus g prime. So in some sense, you are not getting, so f plus f prime comma g plus g prime is not going to be a new point in your conjecture space. So I mean, it is a new point, but like it's somewhat, there is some dependency. So you want to kind of quotient out this kind of things. So so how do we formalize that? So this is the thing that we want to sort of take into account. So for this reason, what I'm going to start by doing is going to define something called the group actions. So on the space of relations. So this is going to be 2 by 2 matrices, which is going to act on our product space. So let's actually formalize this. So so GL2R is going to denote the set of all invertible 2 by 2 real valued matrices. And okay, so I will denote the identity. So these matrices have the property that if A, Fg belongs to C, we will say that, so a particular kind of 2 by 2 matrices, which is going to leave your conjecture space invariant, we will call them C invariant. So, so one, for example, all elements of our 2 by 2 matrices, for example, they will actually not leave C invariant, but a particular class of them will. So to do this, we formally define these maps. So A is a map that maps points in relations to gives you new points in relations, and this is the exact map. So this is how it acts. So these are like 2 by 2 matrices. And what you can show is that this defines a group action. So this kind of maps. So you have a group action from GL to R cross R, this scripter to R, and this is how the group acts. And this so for every such element is going to define a homeomorphism on R. Okay, so it's any such linear map is going to basically topologically not leave R unchanged. So okay, so then the question is like, which linear transforms leave C invariant? Now I have written down two particular linear transforms which are pretty obvious. The first one is pretty obvious. Let's say dilation, so multiplication by positive scalars, for example. So if you do this, it's obvious to see like this thing is going to leave your space of conjectures invariant. But there are some other interesting ones as well. So here is a particular one. So if you look at this particular one, you will be able to convince yourself. So there is a proof in the paper, on the archive paper, that this is also going to leave your space of conjectures invariant. So okay, so the natural question is that what is the largest set of 2 by 2 invertible matrices that leaves C invariant? And actually, this group has a nice characterization. So the full proof is in the paper. I don't think it's particularly helpful to go through the proof in this talk. But okay, so I will tell you how this result actually, the thing that I have on my slide is slightly improved version of what we have in the paper. So in the paper, and as I also mentioned here, so these matrices I said are elements of GL2R. So they are like, these are like real numbers. But actually, you can relax this constraint so that each of them is actually a function. So instead of this being numbers, A11, A12, A21, and A22 can actually now be functions on your on D hat. So continuous functions on D hat. So if you do that generalization, so this is what you can prove. So every element of A, so again, these are 2 by 2 invertible matrices that leave C invariant, but now the matrix entries depend on the point X. So they can be expressed in this form, and you have this nice characterization. So A, B, C are going to be continuous functions, but there is a constraint. So there is no constraint on C. C can be an arbitrary continuous function, but AX and BX needs to satisfy some constraint. So the condition is that none of these functions should be 0 for any X in your D hat. So this is the key constraint that you must enforce. And what you can show is that, so in the beginning we have a set, but you can actually show that this set actually forms a group. And because of this condition, you can also say, again, these are open conditions. So this will be it will have a Banach manifold structure. And so what is this group actually homeomorphic to? So this group is actually homeomorphic to one copy of continuous functions on D hat and two copies of continuous functions on D hat which satisfy this particular kind of a constraint. So one thing that you will realize from this thing is, for example, if your D hat is a connected domain. So if D hat is a connected domain, then this condition means that AX is either strictly greater than 0 or it is strictly less than 0, both AX and BX. If X is not connected, okay, then the thing is like on each connected component of your domain, this condition has to hold, like AX is either strictly positive or AX is strictly negative and so on. So that's all that I want to say about this thing. So anyway, the point is like this result, now the group that we have here on my slide, this is an improved version of the thing that we have in the paper where we just consider real numbers. But now these matrix entries are actually functions, and this is I believe like the I don't know how in what other way you can generalize, but this is a pretty good way to generalize this thing. So how would this actually play out in practice? So in practice, I mean, one would probably choose some kind of basis, so some finite dimensional basis for C D hat, and one will have some finite dimensional basis with respect to which you want to quotient out. So for example, so these are actually details that are being worked out right now, and how to incorporate this kind of symmetries into the search problem, which I'll explain in a bit, is actually the topic of current work. Anyway, so that's the result. Like that's like the big, like the geometrical result in terms of which characterizes the geometry of this space, which is I think interesting. So, okay, so I will just mention one aside to this, which we have also been thinking of, and we have actually done some experiments on this. So far I have defined my space of conjectures to be like f less than g or f greater than g. But as some of you may be wondering, so why do we consider this product structure? What if we just say, f less than g can be converted to f minus g less than 0? So what if we just consider things like functions which are strictly greater than 0 and functions that are strictly less than 0? I mean, this will be an equivalent it will capture the equivalent notion of functions that are positive or negative. So this basically does the same thing. So yeah, that is true. And this leads to a slightly smaller search space, so about 2x basically, once you choose a basis function. So the optimization problem that we have, you cannot do infinite dimensional optimization. So you will choose some kind of finite dimensional subspace, and over those you are going to look for conjectures over this finite dimensional subspace. But okay, but the point is like, okay, you can if you do this, actually this does lead to about 2x smaller search space. On the other hand, and these are questions that we are trying to resolve right now, and so this is a slightly hand wavy. So if the conjecture space has very complicated geometry, maybe the loss function that you have is like, like lots of local minima and so on. So it may be better to have some kind of redundancy in the parameterization space. So, and you should really think of it as a form of relaxation for non-convex optimization problems. So now how this plays out in actual problems, we are not really sure. So far, based on the experiment that we have done, so we have experimented with both these kinds of oracles, where we do search over this like product space versus this like a single copy. And so we do know like performance wise, one is 2x faster, but whether whether having this extra set of redundancy in your search problem has some value for some more complicated conjectures is not yet clear. So we are running some experiments on some different problems and see if we find something where this, this redundant version of the problem has some advantages or not. So, okay, so this is just something that as an aside that I wanted to mention. So, okay, so with that, I think I can talk a little bit about the computational oracle. Again, like it's not particularly helpful to probably go over the precise details of what we do, but at a high level idea, what we are trying to do again is that we want to start from points in a relation space, and we want to kind of find points in the conjecture space. So we start with some arbitrary point, and then we will perform some gradient descent based on some loss function to converge to some point in C. And the loss function is designed so that it is non-zero when fg is not in your conjecture space, and it is 0 when it is in the conjecture space. So okay, so that is basically what it does. And this there is a algorithm that formalizes this. So I don't need to explain basically how one does this to machine learning people. You guys already can probably guess what's going on. Now, okay, so this is the cartoon visualization. So this is courtesy my friend Challenger Mishra, and so you should really think of this like this. So this black box is like your big space of relations, and let's say your conjecture space. This is really not an accurate description because your conjecture space is actually a convex set. Two connected components, and each connected component is a convex set. But I mean, this is a nice illustration of what's going on. So you start from relation space, and then you are doing some kind of gradient descent, and you will reach the conjecture space. So one thing that I will mention, which is important, is that your conjecture space is a convex body, and you can take the closure of this convex set and you will get a boundary. Now, the loss function is designed so that this oracle is going to terminate as soon as the loss function becomes 0. So what it means is that as soon as you enter this convex body, the oracle stops and it spits out a probable conjecture. So what it means is that somehow the oracle is really good at finding conjectures which are close to the boundary of your convex, these two connected components of these convex sets. And but in some sense, that is the thing that you do, because what it means is that, so if I go back a few slides earlier, so I mentioned to you about this epsilon number. So this oracle is going to stop when epsilon is sort of small. But however, if epsilon is large, in some sense, it means that those conjectures are easy. So this method of finding this conjecture has this property that it will tend to pick out conjectures that are slightly harder to find, so quantified by this parameter epsilon. So if epsilon is large, they are much more inside your convex body, and so like it will be harder to. So you basically will not never reach there because there is like you stop closer. So in some sense, this has this nice property that it will sort of kind of give you these conjectures which are close to your boundary. And of course, you can define like how close it to your boundary, define on how small your step length is, and so on and so forth. But okay, so that is one thing that I do want to mention, which I think is an important point to keep in mind of what is going on behind the scenes. Okay, so let me focus on some results actually. So, and I think this is the most interesting part. Definitely the thing that when we found some of them, we were quite happy. So we experimented with this oracle on some number theoretic conjectures. And one of, okay, so in number theory, this prime counting function is pretty important. So pi, so the number of primes which are, so yeah, so pi of x is the prime counting function. And these are some of the conjectures that we have found. And many of them are unproven, some of them are proven, and some of them are obvious. So there's a lot of redundancy in this table. So for example, if you can prove some of these conjectures here in this table, other ones kind of follow trivially from them. But there are some really complicated ones. So I will, so this full list is available in the paper and you can look at it, but I will focus on a few of them in this list, which are very interesting. So number 5 is the famous second Hardy-Littlewood conjecture. So this is a famous unresolved conjecture. And so people don't know if this is true, but computationally this tends to be true for, people have checked it to very large numbers. There is one candidate that is in this list which we were able to prove. So the number 1 is a new conjecture, and this conjecture has been actually proved after talking to some number theory experts actually. So this is the theorem that we know. So this is the machine generated conjecture. So what is the theorem? The theorem is like if xy are positive integers, then pi of xy is greater than equals pi x plus pi y for all xy greater than equals 17. And in addition, the inequality holds for all xy between 2 and 7. So so what it means is that this is true for all xy greater than equals 2, basically. That's what it means. So this thing was discovered using our oracle. So we had basically checked everything up to 10,000 and this was true. And then basically we decided, okay, so let's try to see if we can prove it. And this is one of the such cases that we could prove. So this was, so how does the proof work? So for xy greater than equals 17, you use the Rosser-Schoenfeld formula. And then you enumeratively check these particular cases. So which is this. The thing that it leaves out is the case where, let's say, so let's say x is less than equals to, but y is greater than 17. So there are particular areas in this two-dimensional lattice where we don't know if this is still true or not, but computationally, like this seems to be true. So that we don't know, but otherwise, like this result, the way it is written down is actually correct. So there are two strips which is like outside this sets xy greater than equals 17 and xy in this domain, which we don't know what happens. But computationally, like we checked up to like xy equals 10,000 and this is still true. Okay, so I mean this is a proof that you can find in the archive paper, but it uses the Rosser-Schoenfeld formula. This is for some of you who knows this, great. For others, I mean, there is a formula like this, which basically tells you what pi x satisfies. So it gives an upper bound and lower bound on pi x for some value of alpha. And using this, you can basically prove this result. So I'm not going to go over the proof, but this result happens to be true. Okay, so I think that's a really nice number theoretic result, and actually my collaborator is definitely more interested in facts like this. I will also like to mention, so I am not an expert in this particular area, but this is work done by my collaborator Challenger, and they have some conjectures about Cayley graphs of finite simple groups, and so there are some conjectures of this form which are inspired by Baba's 92 result. Okay, so they claim it's a theorem. So I haven't gone through the proof, but okay, so there is a theorem that they're claiming is true. So I just want, it's okay, but anyway, so these conjectures again you can find in the paper. I'm going to spend a little bit of time at the end speaking about some of my own interests, like why I am particularly interested in this. So my motivation comes from analysis problems actually, and So I will give you one particular problem that I found this will be an interesting thing to generalize. So, so this is the particular problem for Fourier analysis. So what is the basic question? So the question is this: when you are computing the Fourier transform of a function, and let's say this function is well nicely behaved. So let's say it's a Schwartz function in particular. So the definition of a Schwartz function, so I'll just state it for those who don't know it. So these are functions. So an example to keep in mind would be the Gaussian, e to the power minus x squared. So what it means is that not only the function decays faster than any polynomial at infinity. So these are, first of all, these have to be infinitely differentiable functions. But also, like, it doesn't matter which derivative you take, some alpha order derivative of this function, and this is it's true actually for, it's not just one dimensional, but like multiple dimensions, this is true. So it doesn't matter how many partial derivatives you take, the resulting object is also going to decay faster than any polynomial. So that's what the definition of a Schwartz function is. So let's say you want to Fourier transform a Schwartz function, and usually people compute these things on a computer using DFT. So like fast Fourier transform, which is an implementation of the discrete Fourier transform. And then the question is like, how much error do you make? So you get an answer when you compute these things using the DFT. On some, you truncate your grid, you discretize your interval, and then you're computing these quantities. And then the question is like, at your discretized grids, how far are the computed values from the actual continuous Fourier transform? So what's the answer? I mean, this problem has been well analyzed. So for example, in my PhD thesis also, I mean, I have a proof because I needed it for some purposes. So there is one version of the proof that uses the following lemma. So this particular thing is known how to control this. So the general result is that if you have Schwartz functions and if you increase the number of grid points and if you sample far enough, then the approximation is quite accurate. So, but in this proof, you need a lemma that looks like this. So this is a very nice geometrical lemma. So let me talk about this lemma a little bit. So let's say you have this set B, which is like a cube. So all points in RD. So this is a d-dimensional cube. And each side, so the ith side of the cube has size 2b1. So it goes from minus b1 to plus b1. Okay, so you have that, and you define this quantity delta. So this delta is sort of a measure of skewness of the cube. So I mean, this cube could be such that like one side is really long and some other side is really small. So this is going to measure like how big the largest size is with respect to the smallest size. So I hope that is clear. So you have this quantity delta that is a measure of how skewed your cube is. So if all the sides are equal, this delta will be 1. So 1 will be not skewed at all. But delta, like let's say 10 to the power 5 will mean like one side is like 10 to the power 5 bigger than the smallest side. Okay, so now consider this set of points, which is you take out this interior of the cube. So you have this set of points that is outside your cube. And you have omega that belongs to the cube. Okay, so you have points that belongs to the cube and points that lie outside the interior of the cube. So these are two sets of points, x and omega. Then you can prove this estimate. So the estimate is this: the distance to x for any x that is outside the interior of your cube is going to be bounded by this kind of a constant that is 2 times square root 1 plus delta squared d minus 1 times x plus omega. So the absolute value means like the Euclidean distance, by the way. Yeah. So this is a result that you can prove. Okay. Okay. So there are lots of moving pieces in this result. So for example, you have this strict condition on B. So what if so this is the kind of general versions of this lemma that I was trying to, generalize this, and I'm kind of interested in this. So instead of taking this nice convex body, which is like a cube, what if I take something that is other than a cube? So for example, consider this a specific family of asteroids which live in, so let's say R2, but you can do this in RD also. So this is what the general form of asteroids look like. So x by a to the power 1 by n plus y to the power 1 by n equals 1. So let's say, actually n doesn't need to be integer, sorry. So n can be actually positive real numbers also. So that's allowed. But okay, but you can also take integers. So, and then AB is greater than 0. So this is going to be, so for example, let's say this 1 over n, this exponent is 2. So so that doesn't quite work if n is integers, but let's say if n is real numbers, then x, so if a and b are equal, then x squared plus y squared equals 1 will give you a circle. Okay, in the limit when, let's say, n goes towards 0, so so that is going to give you this square, and then if n is 1, for example, you will get this square that is rotated by 45 degrees if both a and b are the same. So yeah, so you have this family of asteroids, and then the question is like, in this lemma, if I replace my b with some kind of body like this, how will this estimate change? So that's right, like really a basic question. And also, for example, I know even in the case of B, these inequalities actually loose, actually. So this is definitely not straight. I know that this is actually quite loose. So this can be actually strengthened. So yeah, so but how exactly to do this? I don't know. And then what is the dimension on the dimension D? So if I change the body, so for cubes, the dimension D shows up as a square root of 1 plus, delta square D minus 1. But if this body becomes something else, then what will happen? I have no clue what is going to happen. So I want a computer to actually help me find suitable generalizations of inequalities of this form. And I'm giving an example. And there are other examples that you can easily imagine will happen. And again, so to recap, like the basic idea is like you have some inequalities that hold, or somebody has proved some inequality, and you are trying to generalize the inequality by changing some of the assumptions in inequality. And how will the inequality change? And I want a system that helps me, a computer system that helps me, at least, even if it is not able to give me exact answers, at least guide my search. So that's all that I'm asking for. So so yeah, so as I said, you have a starting point that you know is true, and you would like to use it to find appropriate generalizations. So these are the kind of motive questions that I have, and I am doing some work on this right now, and this actually looks to be doable. But I don't have any results that I can present today, but this is work in progress. But hopefully in the future, there will be some results of this. So anyways, I'm going to finish up by making some high level outlook and also mention some limitations of where this project is sort of headed, at least the three of us, what we have in mind. So eventually, we would like to find a way to connect this framework to something more exotic, and that is already much more well developed in the computational math community. So like automatic theorem provers and proof assistants that already exist. So how to integrate these things is actually kind of interesting to know. I don't have answers to this, but this is some questions, some directions that we wish to explore in the future. So, okay, as I mentioned already, we would like to extend this framework to handle other kinds of conjectures. So for example, like equality conjectures. So there, one thing that definitely shows up when you work with finite precision problems, basically. So enforcing exact equalities, unless these are like integers and so on. So for floating point, this is actually not super easy to understand. Like if you will get some answers, and whether they're really accurate, if a conjecture is really an equality that you will get on a computer, it's not super easy to figure out what you are getting is actually an inequality, or or maybe actually an inequality. Who knows? So this is something that we would like to understand a little bit better. Okay, so another thing that you can probably guess is if your conjectures, so let's say the kind of inequalities you are looking for has some symmetry. So both sides, so both f and g have, let's say, it depends on some it's a d variables, and there is some inherent symmetry in this function. So maybe the functions are rotationally symmetric, or there is some group action that leaves your functions invariant. How do you incorporate that into this framework? So that is actually an interesting thing to consider. Okay, so yeah, so this is like your inbuilt symmetry thing. And finally, this is slightly, and this actually, I have some ideas which, and basically, there are cases where many inequalities, so some famous ones are isoperimetric inequalities, which is basically bounding volumes of bodies using perimeter of a body. So this kind of inequality, if you want to search for inequalities that look like, let's say, the isoperimetric inequality, obviously you can see like sampling data is itself quite hard for this problem, because, well, what do you need? You need a way to numerically compute areas, you need a way to numerically compute volumes. And because these are numerically computed, first of all, it's not, let's say you have some numerical procedure to do this, you will compute them with some accuracy. So how will inaccuracies in your computed data, so basically the error in your data that you are feeding into these kind of frameworks, how it will affect the conjecture generating process, if it is it stable with respect to these errors. So things like this are not super clear, and they are definitely topics that we wish to explore in the future. Okay, so that's all that I have to say. If you have any questions so we do have a lot of time for questions, and I made it like that. But this email ID is good till February 2024, when roughly I'm graduating in end of this year. And after that, I will be starting as a postdoc in UC Berkeley Math. So my email ID will probably change, but till then, this email is good to go. And with that, I am happy to take questions.